All right, so we are in week 3. So we will create a new folder, week 3, Thursday. And then let's launch VS Code. All right, so last time we have solved a few problems by returning tuples, right? So we didn't print the result anymore. We returned tuples. We went through um, the solution to the permutations problem, to the towers of Hanoi, count change, and so on. So I want to solve yet another problem that returns a sequence, and that will be the prime numbers. And then we're going to go on and learn a little bit about graphics. So today's new file, we're probably going to do two different files today, primes.py. And remember, what are prime numbers? Prime numbers are numbers that only divide. Um, their only divisors are 1 and themselves, right? They have no other divisors. So I'm going to play a little bit with this idea before we reach the solution that we want, right? So the first thing that we want to check is whether a number is a prime or not. So let's define a procedure is prime takes a number n, and it should return true if the number is a prime and false otherwise. Okay, so what would be a very simple solution here? Well, we start with the numbers from 2 up to n minus 1, and if there is at least one divisor, we return false. So we're going to say for I in range 2 to n. Remember, the range is inclusive to the left and exclusive to the right, which means that the last effective value is n minus 1. What we do here is if n percent I equals 0, right? What does that mean, right? N percent I is the remainder of dividing n by I. If that remainder is 0, it means that I is a divisor of n, and we can return false. All right. And if we make it up till the end of the range, if we haven't returned false yet, we can return true. Yeah. So this would be a very simple solution. And let's check that this works, right? So let's write a few verification statements. Print the number. So I'm gonna do a sample so that I can use a boilerplate verification statement. So I'm gonna say sample equals 20, and the number sample so let's phrase it differently. Is the number sample a prime? And we're going to print the result is prime of sample. Okay, and we can do this for a few numbers. So let's say I take number 23, I take the number maybe 97. I take the number 49. All right. So let's see how this works. All right, so is 20 a prime? False. Is number 23 a prime? True. Is number 97 a prime? That's true. 49 a prime? That's false. And you can easily verify these statements. You can go to Wikipedia and check for prime numbers. That page will have a list of quite a few prime numbers, and you can check that 23 and 97 appear there. This is the best solution that we have. Well, what happens is that in the case when n is a prime, we are dividing through by too many numbers, right? Why? Because if there is a divisor between 2 and the square root of n, there will also be a divisor between square root of n and n. Yeah. So it cannot have, right? If a number has a divisor, it cannot have a outside of himself and n. It doesn't have a single divisor. It has at least two, right? Because if k is a divisor, n divided by k is also a divisor, right? So if n is less than square root of n, n divided by k is greater than square root of n, and vice versa. If n is greater than the square root of n, then n divided by k is less than the square root of n. So it turns out, because of that, that we only need to divide by numbers that are less than square root of n, right? So we can essentially reduce this range by adding an extra conditions here and saying, right, if n% I equals 0, or I times I is greater or equal to n, then we can return false, right? As soon as I is past the threshold, right? As soon as I is past the threshold of square root of n, which is equivalent to the square of I being greater than n, then we know for sure that there are no divisors. So by adding this condition, the procedure becomes faster, all right? And the procedure becomes faster, and we can verify that we have the same result. Turns out that that's not true. I square I is greater. Oh, that's really, no, that's really wrong. Sorry. We're going to add a separate condition saying if I square I is greater or equal to n, we're going to say break. Break is an instruction that no matter what, it breaks out of the for loop, right? So we're automatically going out of the for loop, and we're returning true. So under these circumstances, if we run the code, we get the same result. Now let's focus on the problem of returning the list of primes. So we don't want to just check whether a number is prime or not, but we want to return the list of primes of all primes that are smaller than a certain limit, right? So this would be def primes, and we're going to take a limit, right? And one very simple solution would be that we can return a tuple and of all k, right, for k in range of 1 to limit plus 1, if is prime k. Yes. So that would be a very simple solution. And let's verify that this is correct. So we would say that we have a sample. Actually, we only need one verification, so I'm not going to use the sample. The list of primes smaller than 100 is, and we're going to say primes 100. Because if I change the limit to 150, the first prime numbers will be the one that are less than 100, right? So we're repeating the numbers. It makes no sense. So let's see how this works now. All right, and you see all the numbers, just except the fact that 1 is not really a prime number. So we should start the range from 2 and running again, right? You can verify that these are all the prime numbers smaller than 100. Okay, and again we have a problem of returning a tuple, a sequence. We always want to aggregate our results in the form of something that doesn't get printed but actually can be manipulated as a piece of data. So we will continue in this habit of returning aggregated data rather than printing. So this is all about primes. I am not sure whether, okay, there's a chat box here, so feel free to ask questions in the chat. I'm gonna keep checking every once in a while. Can people hear me? Can you? Okay, are there any questions? All right, if there aren't any questions, let's move on. So we're going to experiment with graphics a little bit, right? And we're going to learn how to draw fractals today. The Python language has a graphics package which is called Turtle. I'm going to bring up a browser, and let's go to python.org, and in the docs, let's look for Turtle graphics. All right, so this is all the documentation we need. Let's learn very quickly how to manipulate this, how to interact with the Turtle package. I'm going to go into the interactive mode. All right, I'm going to say from Turtle import star All right, so you can see that the package is imported, and I'm just going to take this entire piece of code and paste it here. And unfortunately, the pasting doesn't work so well, right? So you can see that this instruction has been executed. And as soon as the first graphics instruction is executed, a window emerges on the screen, right? You can see that this little marker here is red, which means that the color has succeeded. And then this begin fill has also worked, right? So we're going to draw a polygonal line, and that is a closed line. And as you see, we need to be getting this figure, this shape here. And what is construed as the inside of the polygon, this is not a convex polygon, so the notion of inside is a bit blurry here. But nevertheless, whatever is construed as the inside of a polygon will be filled with yellow. So I'm going to try to just type in this instruction, this, and this one should work. And now if I bring you here, you would see the animation. We're going to see how we can speed this up. All right, so what is left to do now is to say and fill. And then you would see the yellow being filled up. And there is also a done, which is actually not really necessary. How does the graphics package work? So I think we can say clear. This clears the shape. Let me try to put them side by side so that the animation is visible, right? The interaction is very easy, right? If I say forward and something like 100, right? The turtle, right? The little marker that you see is called the turtle. Is like the turtle is walking around, leaving a trail, right? So if I say forward, it'll just go in whatever direction it is pointing, and it will go the distance that is indicated. Then we can say left of, let's say, 90 degrees, right? And you can see that the turtle is turning, and then I can repeat the forward, I can repeat the left, I can repeat the forward, I can repeat the left, forward, and left, and we have a square. All right, and we can draw all sorts of shapes. So we're going to try to draw very interesting patterns called fractals. We're going to try to do that today. So let's see how that can be done. If I exit the window should close automatically. Let's go to the text editor. And I am going to start with a rather unusual shape. All right, I'm going to start a new file, call it fractals.py. All right, and we're going to do as before from turtle import star. We are importing all the functions inside turtle. By doing this, we now have access to forward, right? Forward is one of the procedures that exist inside the turtle package. So let's define our first fractal, and we're going to do that incrementally. Fractal 1, all right? And we're going to have an argument later. For the time being, let's not worry about that. And I'm going to do something very simple. I'm going to say forward let's say 100. All right, then I'm going to say left 45 degrees, then forward another 100. Should I make it 100? Should I make it, I don't think it should be 100. I think it should be 100 times square root of 2. So in order to have access to a square root, we're going to say from math import sqrt. So this makes the sqrt function available. Then I'm going to turn right 90 degrees, then forward another 100 times sqrt2, and then I'm going to turn left 45, and I'm going to go forward another 100. Okay, and I would like to run this fractal, right? So in order to run this fractal, I'm going to play another trick. I'm going to play another trick. So save this. And in going here, I'm going to say Python. So notice that there's no verification code. Python 3. And I'm going to say -i fractals. All right. So this file has been read into Python, and now we are at the interactive mode. So I can actually invoke the function 1, and then we're going to see the drawing, and because we are in interactive mode, we have not left and this window has not closed. So this is the shape that we are drawing. It's a bit off to the right, all right? And it's a very simple shape, and you might be wondering, why are we, bothering to do this? So we are bothering to do this for a very simple reason. So I want to ask you the following question, right? So imagine now that each of the segments inside this drawing that make up this drawing are a scaled version of the drawing itself. All right? So instead of drawing a straight line here, I am drawing a scaled version of the drawing. So I'm going a little bit forward, then up, then down, then further over again. And then this segment here, I'm doing the same thing. I'm going a bit, along the direction, then turn a little bit to the left, turn a little bit to the right, go forward again and reach here, right? So each, we can do this, right? Replace every segment by a scaled version of the actual curve, all right? And then we're going to get what we call the level 2. What we have now in front of us is the level 1 fractal. We're going to get the level 2 fractal. And then guess what? We can do that very same thing recursively. So I can take this, and every segment in the level 2, I can make it a scale version of the level 1. That's going to lead me to level 3. And then in every segment in level 3, I can make it a scale version of level 1. And I can continue on and on until potentially infinity, right? So mathematically speaking, we can do this until infinity. There is a limit. We can think of the limit of n going to infinity, the level going to infinity of this curve. What does this curve become? Obviously, we can't make the computer compute till infinity, but actually if we go to a level that is high enough, maybe 7, 8, 9, it will already be very close to that limit, and we can sort of envisage. And the shape will be somewhat surprising, and so it's very hard to predict what is going to be right now. And that's what we call a fractal. So let's see, how would we How would we get that version? Well, this curve has a very good property. It ends, right? It ends at the same angle as it begins. So it begins at an angle of 0 and it ends at an angle of 0. So this is a very important property that we want to maintain. It's sort of incidental here. If you draw other fractals, you will have to make sure that this is happening. And then we're going to add a level here. And then the level 0 is just a segment, right? So the level 0 of this would be a segment starting here at 0 and ending at somewhere around probably 400, right? This is probably 400 long, all right? And we have a level. So if the level is 0, all we have to do is go forward of 400. Yeah. And then else, right? And we want all this to be the else part. So instead of doing forward, I'm going to do fractal 1. All right. And this will be n minus 1. And then we're going to left 45, fractal 1 again. And this will be n minus 1 again. And this would be fractal 1 again. And this will be n minus 1. And this will be fractal 1 again. N minus 1, right? So now we're noticing that, and it's not n minus 1, I'm sorry, it's level minus 1. Same here. Same here. And same here. And there's another thing that we need, right? Because we are saying that it's a scaled down version, right? So we're going to need to add a scale. All right. So notice that when we go to level 1, the segment that I'm going to use is exactly 4 times smaller than the original. So I'm going to have here scale divided by 4. Right? And when I do forward 400, I can't have 400 here. I will have to have something like 400 times scale. And we're going to start initially with a scale of 1, and then the scale will keep going down. Fractal 1 level, right? And everywhere, actually, we would have, so this is not scale divided by 4, but it's scale divided by 4 times square root of 2. Divided by 4 times SQRT2. Then same thing, divided by 4 times SQRT2. And divided by 4 times SQRT2. Okay, so let's repeat what we wanted to do. I'm going to stop this. I'm going to exit here. I'm going to start this again. And we're going to do fractal 1. So let's do level 1 with a scale of 1. And we see that we're getting exactly the same drawing as before, right? One nice thing we could do is set the position by 200 pixels to the left. And I should find out how that can be done. So I think there's I think we can do something like pen up. So I'm going to clear pen up, and I'm going to backward. .400 pixels. Okay, let's do another backward 400 pixels. Okay, so might be too much. So if I do now, so now I have to put the pen down. And then now I can draw the fractal. Okay, so if I clear and I move backward by 200. Oops. All right, so the meeting will end in 10 minutes. What I'm going to do is end the meeting just a few seconds before and restart the meeting, and then everybody can connect. But there's still 10 minutes left of it, so let's keep going. So where was I? Clear. Okay, and now I can do the fractal one-on-one, right? So now the fractal appears, I would have hoped that it would appear a little bit more centered, but all right, let's just clear, pen up, and I think I can say set position. -200 and 0. Let's see if that works. All right, and then, okay, this one looks centered. Let's put the pen down. And we can do the fractal. And this one looks centered. So we can do this again and clear. So let's see now what happens if we do fractal and we increase the level to 2. Right? So notice now how we still have the old drawing. So we have a segment from here to here, another segment from here to here, another segment from here to here, and another segment from here to here. But each of the segments is a scaled version of the curve itself, right? So it has become a little bit different. And we can keep going. For some reason, it's a bit asymmetric. I'm not sure why. Let's take another look at the code. Did we do something wrong there? Oh, this one should not be square root of 2 here. Okay, Control D, restart. So we want to do a set pos. All right, and then we want to clear. And then fractal to 1. Okay, this one is symmetric. So we can again set pos to the original position. We clear. Let's see the level 3 curve. All right, so we get more and more detail. Obviously, it's slower and slower. I will show you the trick of speeding it up, but let's do one version again before we go there. So clear level 4. So you're noticing now that the length of a segment is very, very small, probably very close to the size of 1 pixel. As soon as a segment becomes the size of 1 pixel, we won't be able to see any further detail, right? So at level 4, we already have a pretty good um, view of what the limit would be, right? Between level 4 and level 5, we won't see much of a difference. Okay, so this is the general principle of a fractal, right? We take a open polygonal line, a line made up of many segments, and then um, the what we do is take every segment and make it into a scaled version of the curve itself, right? And that will result in a lot of smaller segments, which we can then each of them turn into a scaled version of themselves. And we get this very interesting shapes. You can, in principle, start from anything. You don't need to take a specific shape. You can take irregular shapes. So I'm going to try to do some every time when I do fractals, and I'm trying to create one that is completely new. I'll tell you what, this is a good point, a good time to stop the meeting. So I'm going to stop here and restart. So I'm going to stop the sharing and end the meeting. All right, so let us start an attempt to create a completely new fractal. All right, so we're going to define fractal 2. So we're going to have the same principle, right? If level equals 0, forward, and I'm going to have something times scale. I'm not quite sure. Maybe let's do 500 or 600 times scale. Else, all right, and let's try to make something a little less regular. So all right, so let's go fractal 1 level -1 and scale divided by 2. All right, then let's turn left 135 degrees. Let's go fractal, sorry, not fractal 1, fractal 2. -1, scale divided by 4 times SQRT2. So I'm going to turn to the left 45. No, another 135 degrees. I'm going to do a fractal 2 minus 1 scale divided by 2. And the good part about it is, let's see what we have so far, right? So I'm going to go here. And obviously I have to exit. I have to start again. And I'm going to do set position minus 300. All right. So that it's centered. It's 600 in width. I'm going to clear, and I'm going to do fractal 2 of level 1 and scale 1. All right, so this is what we have so far. What we want to do is reach this point, which is 300 and 0, right? And facing to the right. So let's try to do that. Let's try to do that. So we're going to turn now another 135 degrees to the right. Oops. So we're going to turn 135 degrees to the right, to the left. To the left. Then fractal 2 level minus 1 scale divided by 2 times SQRT2. All right, let's see what we get with this one. All right, so let's just come down and end. So we have to turn again 135 degrees to the right this time, and then we turn 90 degrees and finish. Or we turn 90 degrees to the right, and we go scale divided by 4. Right, so the easiest way to finish, so it's not too long. So we're going to go right 90, and then fractal 2 level scale divided by 2 times SQRT2. And then we have to turn left 45 degrees. Okay, so let's see what we have now. go too far? Maybe we went too far. I think we went too far. Yeah, we went too far. So we should go only scale divided by 4. So scale divided by 4 here. Right, so now again we're going to try to see the next levels, right? So every segment becomes an instance of a scaled instance of the whole curve. Right, so this will probably be quite interesting. Notice the fact that and quite frankly, I haven't done this before. I have no idea what's going to come out. So notice how the arrow ends up pointing in the same direction. So this is a very important property. So I'm going to set the position. I'm going to clear, and I'm going to run fractal of level 2. All right, so this is level 2. So let's see level 3. All right, so you can see that it takes longer and longer. And then let's try to figure out a way to make it faster. And I'll try to explain how this package works in terms of speed. The drawing engine tries to draw on what is called inside the memory, right? And then the screen gets updated. The content of that memory is shown on the screen with some frequency, right? If we reduce the frequency with which we are showing, we will have less of a feeling of animation, right? The animation is going to go lower quality. Nevertheless, the speed of drawing is going to increase very much. So if we go here, we're going to find out the instructions that are right. So it's these ones, right? Delay, tracer, and update. So let's try to understand how we can use these. So we're going to reduce the delay. I think currently there is a delay between every two drawing operations. So we're going to reduce that delay. And I'm not sure, I'm going to set it to 0. And then we're going to reduce the frequency of updates. And I think this is done with tracer. So the tracer will reduce the frequency. So we're going to say n, we're going to set n to very large. And we're also going to set the delay of 0, which actually is exactly as calling this delay. So we're going to say tracer of 1000 and delay none. Actually, we only need to say tracer. And then at the end, we have to perform an update. We have to force an update. So I'm going to say tracer of 1000. And at the end, we have to not forget to perform an update. So let's show this, and let me now call fractal for one, and then I'm going to say update. So now notice it's a lot faster, yeah? So we see the level 4, and then let's do this again. Let's try level 5. All right. So this is level 5. We can also do an update here. Level 6. Okay. Another component we can add is color. So let's try to do that while we are going to lower and lower levels. We're going to just use a pen color and not a filling color. And let me remember exactly how that is. How we do that. We just have a color red. So I think color can have just one value. Let's look at color. Oh, there's a pen color, right? So we have a color, but we have also a pen color. So let's use that one. So we're going to say, we're going to start with red. And do we say that, okay, name of the color, yeah. So red, pen color, yellow, pen color, blue, pink, pen color, green. Again, I'm picking the colors very randomly, and I'm not very good in general with colors, so we might get a complete mess. Never mind about that. So let's do this. Let's not forget to do the tracer 1000, and let's keep going. Let's try level 7. What we get. Okay, so now you can see a bit of color. So the updates that we're seeing are every 1000 segments. And you can see that it's still pretty slow at this point. Again, I can make it even, I can make the tracing even faster. I can increase that value even further. Yeah, so this is a fractal. Level 8, but before that, okay, let's do a 10,000 here. So you can see that the granularity increases. Unfortunately, it's not a very interesting shape. You can try experimenting with the configuration of the segments till you get a more interesting shape. the time taken to complete the drawing is exponential. So in this case, because we have um, how many segments? 1, 2, 3, 4, 5, right? Each new level is 5 times longer, takes 5 times longer than the previous level. So this will keep going because it has to actually reach this point, right? So this part has not been even started yet. We'll have to wait for that to happen. And then this is also quite compute intensive. I can feel the laptop is right now sitting in my lap, and I can feel it getting a lot hotter. Just because we have requested this piece of very intensive computation from it. Okay. Any questions? Any questions? All right, so in order to be able to run this, I think we should stop it. In order to get this to run, we're going to add a verification um, code here. Let's just stop this. All right. So we're going to essentially add all these 3 pieces of code. And we're going to run, so we're going to leave it at 1000. And we're going to run level 6. And we want to instruct the computer to wait instead of exiting, because exiting will close the window. So that is done via would this listen to that? We're going to just put a sleep, I think. Does Python have a sleep? All right, quickly, Python sleep. All right, import time. That's what we need. So we're going to go here, say from time import sleep. And we're going to sleep maybe 10 seconds at the end, right? So now if we run the Fractals code, we're going to see the level 6. We're waiting for 6 for about 10 seconds. And, oh, we have not done the interactive mode. So we've done still the interactive mode. Let's not do that. So if we run this, we wait for 10 seconds. And the program ends and the window closes, right? So this is the code for tonight. Are there any questions? If not, the code will be uploaded shortly, as well as the video. And you are welcome to revise the material and ask questions later. Thank you. Good night.